Okay, now let's talk about VLANs, or virtual local area networks. Now the concept or the purpose of a VLAN is very much the same, or kind of goes hand in hand with subnetting. We want to take a large network, break it into smaller subnetworks, and we want to do that to, as we talked about, to increase security, reduce congestion, reduce collisions, and so on and so forth. Well, we can do the same thing with a virtual LAN or a virtual local area network. Okay, so as you break a network up into smaller networks, we can assign each into its own VLAN. All right, so there are two different layers of the OSI model. A VLAN is a layer 2 concept. IP networks are a layer 3 concept. So if we have our switch, as we looked at before, and then we take a look at adding or subnetting that down, we can break it into separate subnets at the IP layer, or layer 3 of the OSI model. We can then assign at the layer 2 of the OSI model separate VLANs to coincide with those IP subnets. All right, so VLAN 10 as an example could use 10.1.1.x. All right, so the 1 network denoted here in orange, that would be assigned to VLAN 10. VLAN 20 would have 10.1.2.x, and then 3 and 4, so on and so forth, okay, .3 and .4x. So in other words, a host at 10.1.1.20 as an example would be in VLAN 10. A host in 10.1.2.30 as an example would be in VLAN 20. VLAN 30, 10.1.3.23, VLAN 40, 10.1.4.45, just as an example. So those individual hosts cannot communicate with each other, all right, because again, they're in separate virtual local area networks. They would need a router to communicate. So we take that one large IP subnet, or that one IP network rather, use routers to communicate between the two, increase security, reduce congestion, and reduce collisions. Okay, the next concept is network address translation, or NAT, and that was basically allowing us to mask or hide the private IP address that we talked about previously. Remember, class A, B, and C each has a private IP address range. We're able to hide that address range on our internal network as it goes out to the public or external network. All right, so we can basically have as many IPs as we want behind our firewall, behind our connection out to the internet. That edge device will act as a NAT router, okay, network address translation. So all of our internal IP addresses will appear to come from either one or more external IP addresses that were assigned. All right, so a NAT example. All right, so here we have 10.0.1.15. Okay, it's a /24. That's on our internal network. Okay, say we have a PC here that's going to send some information onto the wire. It's going to traverse our switch through the router, through our firewall, and hit the edge switch, which connects us to the outside network. That edge switch has external or public-facing IP addresses, and so when it hits the outside world, it appears to be coming from 21.1.15.x, whatever that x is, the host address. That's just an example. It could be assigned whatever our ISP gives to us, right? So it doesn't have to be that number, it's just what's assigned. All right, so just some additional information. It has a subnet mask of 255.255.255.240. That gives us 16 IP addresses with 14 hosts available. So in this particular example, the range would be 25.1.15.0 through 25.1.15.15. All right, it gives us 16 hosts, 0 through 15. The usable addresses, as we talked about, would be 1 through 14. Because remember, 25.1.15.0 would denote the network ID, the network address, and 25.1.15.15 would be our broadcast address. So in other words, if a host on that network wanted to send out a packet to everybody on its network, it would send it to 25.1.15.15. All right, so that's why we can't use those two. But our hosts can take between 1 and 14. All right, so we send a packet out onto the wire, and you can see it starts at the one PC internal, goes through our switch, goes through our router. When it hits that external edge device, that router then strips off the internal IP address and then adds the external IP address and forwards it out onto the network. Okay, so we have two different things we can look at here. We have NAT and then we have PAT, network address translation, and port address translation. NAT is a one-to-one mapping, not necessarily scalable in a very large environment, just depending on the IP block. If we have thousands of internal hosts and we only have maybe a dozen or so, a couple dozen maybe IP addresses, we're not going to necessarily be able to do a one-to-one mapping. So we can do something else referred to as PAT, or port address translation. So the firewall, the NAT/PAT device, keeps track of internal requests and then maps them to a single external IP. All right, so we use ports, in other words, to keep track of connections and traffic. All right, so an example. On our internal network, we have Jack, Emily, and CJ's PCs. You can see there's 1.22, 1.15, and 1.20. All right, it's a 10.0.1.0/24 network. Goes through our firewall to the external or our edge router. The internal adapter will have an interface on that internal network, 10.0.1.1. The external adapter would be an IP address that's assigned to us from our ISP. So the external adapter would have 25.1.15.17. Okay, if we take a little bit deeper example here, or deeper look rather, at our port address translation or our PAT example, what we have is a couple concepts. We have our internal client at 10.0.1.22 who wants to communicate with a web server and basically visit a website. Okay, that web server is going to sit at 204.50.18.88. Now there's a couple of other concepts that you need to be aware of, and they're color coded here. We have our inside local address, our inside global, our outside local address, and our outside global. All right, so we have our router in the middle. That's going to provide port or port address translation. That's got an IP address internally, our default gateway in other words, of 10.0.1.1. It has an external IP address of 25.1.15.17. All right, so as we go through the internet, we're going to request a web page. Well, that is going to be directed to our router, okay, the PAT router. It's going to go out, and as we see here, the source IP address is going to be 10.0.1.22. The port that is randomly assigned, all right, that is going to pass through. The router is going to understand and say, all right, that inside local address needs to go to an outside local address, which is the 204.50.18.88. So in effect, what it does is it strips off the internal IP address and replaces it with its own external IP address. All right, the destination address and the destination port do not change. It's going to be 204.50.18.88 on port 80. What changes is the internal or the source IP address, and also the router is going to change the port potentially. If the port that the client has assigned is not already in use, it can go ahead and use that port. Okay, that's 7100. But let's assume, just for the sake of this example, that that port is already in use because we have lots of other clients that sit behind this router that need to communicate with the outside as well. So there's a chance that that port 7100 might be in use, which is why you see in the example here, we have our source IP address now of 25.1.15.17 with a source port of 7150. Destination, as I said, is the web server. The web server is going to receive that IP address, or that request rather, from that IP address. It will respond back to the external interface of that router. Okay, so the response is the source IP address of 204.50.18.88 with a source port of 80. It's going to reply back to the destination of 25.1.15.17 with a destination port of 7150. The router, which is providing our PAT port address translation, understands that anything coming in on port 7150 needs to be sent to our internal client. So what it basically does is it strips that off again, passes it through, and now we have our source address of 204.50.18.88 on port 80 now goes to a destination of 10.0.1.22. Okay, so to try to wrap this up into very quick terms, we have our internal client trying to reach the internet. So they communicate through the router. The router is going to strip off the internal source IP and port, replace it with its own, okay, and put a randomly generated port, send it out to the internet. The internet then replies back, sends it to the router. The router passes it through, translating it back to the original port, and the original IP address sends it back to the client, and all is well with the world. From the internal client, all it sees is it's communicating with the outside world. The outside world, or the web server in this case, all it sees is it's communicating with the public interface on the router. It knows nothing about the internal addressing scheme that's taking place here, so it increases security by allowing all of our internal clients to be hidden from the internet and be hidden from external view as far as what the IP addressing scheme and so forth is, and it allows that router to basically have multiple clients on the internal network communicate through a single IP address, because it's, again, replacing the source port with its own port table, so they can communicate back and forth and say, okay, I know this one needs to go here, this one needs to go there, and it maintains that mapping or that translation, so it knows how to direct those responses back to their appropriate clients.